Hey there, guys. It's time to talk about some air quality. Some of these things are going to be things you've seen before, these pictures, but you know what? It's always fun to look at smoggy air once again. This is London, the London smog, if you will. Here we have my hometown on fire, or at least the river. Check out some fabulous combustion products just wafting into the air. You can imagine what the ozone was like that day. Although I have to admit, it doesn't get sunny very often in Cleveland, so maybe there's not much ozone to worry about. Just kidding. The sunlight still filters through the clouds, at least the wavelengths that matter. So yeah, these are great shots from the 1968 or 69. It caught on fire several times, but obviously fires are a major air pollution issue. We know this, of course, today, especially with wildfires in forest or forest fires in California and Indonesia. Incidentally, one of the biggest sources of carbon dioxide pollution, in addition to these other things, are the burning of forests in Indonesia, where they're putting palm oil plantations. Right, almost a quarter of the world's CO2 comes out of palm oil plantations. So next time you go and look at the ingredients in your food, check it out. Palm oil is everywhere. And guess what? You buy that peanut butter, almost every single jar of peanut butter in the store has palm oil in it, and you're deforesting. Not to make you feel bad or anything. So here's some pictures of the good old U.S. of A. Once upon a time when, well, I won't say it. I was just going to say when things were great, right? So here we have lovely smokestacks, factories, but the economy is working, obviously. Here, we have a family living close to their workplace. In fact, almost a part of their workplace. This was a day. This was a time when we didn't scrub the smoke coming out of smokestacks. It didn't matter because we didn't. What we didn't know didn't hurt us. Kind of like before we knew about germ theory. The plague was just the plague. It was a result of any number of things, but germs until we figured that out. So it's, it is what it is. It's nothing hurts you until you know about it. Anyway, here's of course today in China we have a similar problem. So not just China, other places. So let's talk about some of the results of these things. So here are this goes back to I think it's 2011, the number of pediatric ER visits as a result of correlated with asthma prevalence. Of course, a lot of pediatric ER visits, or large significance of them are due to asthma. You can see in certain places, California, of course, for California, it's an air quality issue largely. You got lots of smog buttoned up against mountains. Texas, it's oil production. Florida, largely against smog. Same with New York. Ohio, Pennsylvania, Michigan, Illinois, and so forth. That's largely coal-fired stuff, along with some of the cars and stuff. But having grown up in Ohio and being somebody who has a bit of asthma myself, I often think about these things. But nobody wants to drag their kids to the ER to go and get checked out for like shortness of breath. Now, another problem, another air quality issue, of course, one of these asthma issues is particulate matter. We haven't talked about particulate matter. We'll talk more about it in a minute. But particulate matter comes in two varieties that we really measure: 2.5 micron, or this is a concentration in micrograms per cubic meter, and 10 micron. And 2.5, 10 is about the width of a human hair, and 2.5 is obviously about a fourth of that. So it's these are things that get into your lungs, into the alveoli, and make it difficult for you to breathe. And some of these things, asbestos fibers are not included in these, but breathing things into your lungs, some things you can't get back out. So black lung disease that coal miners used to get is a good example of particulate matter that gets lodged in the lungs and never comes out, ends up with scar tissue and so forth. Briefly, our atmosphere, though, overall is a bulk thing, has a long history to it. This is a lovely graph. You'll want to pause this and just take it in and stare at it and just love it for a little bit, because there's some great stuff here. So if you look back to 4.5 billion years ago, the beginning of the Earth, you have your first atmosphere, which comes from the largely the outgassing during the differentiation process of the interior while the Earth is still molten. So all the dense materials descending to the bottom. But this early primordial atmosphere doesn't last long. The solar wind blows it away because there's not yet a magnetic field to retain it and to sort of deflect the solar wind. Eventually, of course, the Earth begins to cool enough, and now you have a solid inner core and a liquid outer core that allows, by this time, over here, for the retention of an atmosphere. And this atmosphere now is mostly volcanic in nature. It's not until all the way over here that we start really producing, actually over here, but really up here, really start producing a lot of oxygen. And guess what? This is the Earth's third bulk atmosphere. So you have atmosphere number one, gets blown away by the solar wind. Atmosphere number two is really, really volcanic. That lasts a good long while until photosynthesis evolved somewhere around here about 3.8 billion years ago. And now suddenly we were ramping up oxygen, especially in the oceans, and then eventually in the atmosphere. And there's good rock record evidence for this. And then, of course, back to modern levels from about the Cambrian period on into today. So, life has altered the planet, of course, and life at this time is microbial. So there's no reason why life couldn't still alter the planet, i.e. humans, right? So all other characteristics of the atmosphere, of course, we have different layers of the atmosphere. We're mostly concerned with the troposphere, although when I was a kid, it was stratospheric ozone. We had the Montreal Protocol that Reagan signed. It was a big international thing that, sort of put limits on chlorofluorocarbons and other ozone-destroying chemicals that would make their way to the stratosphere. And we've been closing the ozone hole ever since, because that was going to be the near and present danger at that point. Now we're back to just basically criteria air pollutants as well as global warming pollution. But the atmosphere has a number of layers, and you'll note that let's see here. Well, the temperature is not on here. But you can see the atmospheric density decreases as you go up into the atmosphere. I was going to say the temperature decreases until you get to about the thermosphere, and then it increases again, partially because of the presence of ozone up there. But it's interesting to note that of the sunlight that makes it through the Earth's atmosphere, most of that comes in the form of near ultraviolet, which doesn't get blocked by the ozone in the stratosphere. The other UV does. And then visible and infrared, including the really red light, all the red light, including radio waves and so forth. So if you're going to set up set up some astronomy on the surface, it needs to be either visible or radio generally, or near infrared. So, when you talk about ozone production down at the surface, you're talking about visible light, infrared, and radio waves. And so the most energetic of that light is the visible. And then, or actually the near UV is more energetic, but that's a smaller proportion of things. So we're anywhere from 300 nanometers on up all the way past AM radio wavelengths and so forth, which are in the kilometer length for, so 300 nanometers on into kilometers eventually. So that's a fairly large amount of the Earth's magnetic or electromagnetic input, the sun's electromagnetic output, but it's still not all of it because there's a lot of the really high energy stuff doesn't make it through. All right, so, and of course, Earth has an atmosphere and a certain temperature regime that allows it to retain certain gases because the Earth's escape velocity is higher than the ability of these gases to speed up to that point and be get out. It's like helium and hydrogen, for instance, can easily leave the Earth's atmosphere because they're able to move beyond the escape velocity necessary to do so. But they can't do that on these four planets here: Uranus, Neptune, Saturn, and Jupiter. So we're able to retain all these gases that are on these lines here. You could call them isovels. Below the Earth here, meaning same velocity. So one way of putting it. Isovel, I think, means another context, another situation. But okay, so another way of looking at the Earth's atmosphere and its layers. So anyway, of course, this gives you an idea of where some satellites tend to orbit. The International Space Station's up here about 300 kilometers. Sounding rockets from Wallops don't really necessarily get too far out of the main part of the atmosphere. But again, right down here is where we're mostly concerned about concentrating our efforts and thinking about air pollution. So the troposphere itself is not just a single layer. I mean, it's probably the most complex layer of the atmosphere in that, of course, we all know that weather is driven primarily by temperature variation around the planet, which of course drives planetary winds, Coriolis, including the deflection of the winds due to the rotation of the Coriolis effect and so forth. But the uneven heating of the surface is the big thing. So oceans heat up more rapidly than ice does because of the albedo. And then that heat gets distributed by ocean currents. And anyway, it's very complicated. But there is something called of course, the tropopause, and that, of course, is closer to the Earth at the pole, only 20,000 feet at elevation, and about 30,000 feet of elevation up here near the equator. And that contains most of the mass of the atmosphere in terms of mass, not thickness, but in terms of mass. The part where it really gets complicated is down here below what's called the planetary boundary layer. And most of the clouds hang out above that boundary layer, but down below the boundary layer, things are really turbulent, and you get the orographic effects of things, and the temperature variations are much more drastic. But wind is much more drastic, and so meteorologists are looking at this area, but they're also looking at areas above that. So anyway, so that's all important. It's all important to understand where we're talking about the troposphere, but we're really talking about ozone and CO2 and other things and how they affect us down here in terms of actual air quality. Although once things get up here, they transport much greater distances much more rapidly. So within the troposphere, below this planetary boundary layer, as the sun rises, here's noon, here's midnight, here's noon again the next day. During a 24-hour period, at night, or I'm sorry, during the daylight hours, you'll have a mixed layer where there's a lot of mixing going on in the atmosphere with convection cells and things of that nature. At night, things calm down. You end up with a stable boundary layer near the surface that's cooler, and a residual layer left over from the daylight hours. So this is important because at night, things are very different at night in the atmosphere than they are during the day. You've already looked at that with your data, your ozone data. You've noticed that there's differences between day and night. This is part of what's going on here. Now, NASA, of course, has, in their wisdom, developed satellites that look at this stuff. So this is from the Calypso satellite back in 2017. And you can see clearly right along here that the top of the planetary boundary layer of the troposphere, 30 kilometers up here is roughly where the top of the troposphere is. But, one can make an argument beyond that. But really, this is where all the action is occurring, is right down around here. And especially down here, you can see how uneven things are. So this is kind of cool. Okay, ozone. You've talked about ozone a little bit. You've studied it a little bit. I mentioned something about plants and the closing of stomata, as well as how ozone can disease a lung. There's a nice diseased lung from ozone, an asthmatic lung. And here's what happens to plant leaves. So you can tell if ozone levels are high by looking at plant leaves. Just you don't even have to have a monitor. You can kind of just go look and see what's going on with leaves. Because they begin to behave like it's nighttime. They close off their stomata and they can't take the ozone in. It's too big of a molecule. So this is looking at asthma again, asthma prevalence. Strangely enough, West Virginia didn't report any data. But these areas here, of course, this is the old Rust Belt area of the country, and we're not far from that. We're just downwind from a lot of that. So, but you can see where a lot of the states where there's, you have a lot more asthma. And ozone, of course, is a contributor to the making of asthma worse for people. Power plants are a big part of that. And, it is what it is. We, in our modern world, we have to have electricity. And one of the cheapest ways to do that is to use coal and, of course, natural gas. Natural gas is cleaner in many ways, but it still has combustion products. So here are the national mortality effects from power plants. And perhaps interestingly, again, here look at where we are. I mean, people are dying from power plants. If you go by what this is saying, of course, but this is just by county, and of course, we're looking at per 100,000 people. Counties that are really deep red are greater than 14 people. Of that 100,000, more than 14 of them have died from direct relations or directly breathing in power plant gaseous effluent combustion products and the results thereof. So, this area of the U.S. has historically been fueled by coal, and from Pennsylvania, Kentucky, West Virginia, and the Panhandle of Virginia. So you can kind of figure out why this is the case. And of course, there is actually research that suggests that some groups of people are more susceptible to asthma than others. Particularly people of an African-American descent or having come out of Africa. Why this is, of course, I can't go into that right now. I don't have the answer for that. But this was one research article that showed a disposition genetically. Okay, so air is largely composed of nitrogen and oxygen, followed by a bunch of trace gases and some CO2. And this is important because there's a lot of nitrogen. We like to pull that nitrogen out of the atmosphere and make it into fertilizer and things of that nature. It's important for us to have oxygen, but you'll note that it's not a purely oxygenated atmosphere. We know that wouldn't be good because lighting a match would be more difficult. Well, you'd light a match and you wouldn't be able to survive it. Well, at least in an enclosed area. We learned that in the Apollo mission, where all the astronauts died, and it was Apollo 8, I believe, where the capsule caught on fire on the inside because they had a 100% oxygen environment, and then they had electrical spark. Okay, but an air pollutant is simply any substance emitted or produced in the atmosphere as a result of human activity that's in a large enough quantity to cause problems. And of course, this can be direct or indirect. These problems can be direct or indirect. And that largely goes without saying. Examples of direct issues. Here's an example of 1948 in Donora, Pennsylvania, where 20 people died from this pollution event from industrial facilities that we had stagnant weather conditions and didn't blow the smoke out of the area. People ended up dying. 1952, the famous London smog. There's a before and after, if you will, or what looks like today. Nelson's column looks like today versus the 1958 smog. But these are bad for health. So, we finally recognized that this was the case. Began in the 1960s here in the U.S. We started to be able to measure these things, and of course, actually since 1948 when that event in Pennsylvania occurred, it was recognized there was a need to regulate these, to sort of do something about air quality. So the first Clean Air Act was actually passed in 1963, but it wasn't until the 1970 Act under Nixon that actually gave the U.S. Environmental Protection Agency, which was brand new, the authority to regulate this air pollution, and then identified 6 criteria pollutants to monitor, which are these. And I had them listed on the board today. We've been looking at ozone, and I found some good data sets where we can look at some of these other ones and kind of see what they've been doing in various places, see if we can see some trends in between them and so forth. Yep, more spreadsheets. Yes! I love spreadsheets. Okay. So a brief overview. Ozone, of course, formed by the interaction of sunlight with other pollutants. You know that now. So you should be able to pick up a relationship between ozone and nitrogen oxide or carbon monoxide or other VOCs. Nitrogen dioxide comes out of car exhaust and electricity generation. So, but you first producing nitrogen monoxide during combustion that then gets converted into NO2 in the atmosphere when it combines with another oxygen. But it's a very reactive. NO is pretty reactive. And carbon monoxide, of course, which is also produced that way. Particulate matter is that really small stuff that you can breathe in, comes from a variety of things. It can actually be liquids that are floating around the atmosphere. Technically, water droplets are a form of particulate matter, and one can make an argument. Not a dangerous one, but then, of course, lead. Lead was more of an issue when I was born. They were just getting rid of lead in the gasoline. We'll talk about that more later. And of course, sulfur dioxide, which comes largely from burning coal, the major combustion product. Anyway, then we have primary pollutants, which are emitted directly from various sources. And then there's secondary pollutants that result from chemical transformations in the atmosphere. Ozone falls in this category, as you now know, along with some others that you can see listed there. But the primary pollutants are really nitrogen monoxide, sulfur dioxide, carbon monoxide, and carbon dioxide. And it's from there that they are catalyzed into other things. So again, natural versus anthropogenic. So these compounds exist naturally. We're just elevated because of anthropogenic activity. Natural sources of some of these things include termites, lightning, and trees. Again, we're not talking about massive amounts here, but we're talking about trace amounts of these gases, and it's significant. Anthropogenic sources include point sources. We already talked about that. Non-point sources or aerial sources. And of course, on-road and off-road. These are pretty straightforward. I think you've learned about these before in other places. So the EPA has developed an air quality index, which we have time. We'll do some AQI calculations. But the bottom line is the index is based off of the 6 criteria pollutants in the air. There's baselines for each of these criteria pollutants, and then of course you're taking actual measurements, and then there's a simple little equation you use to come up with the index. And the index generally is from 0 to about 300, And when you get closer to 300, it gets to be hazardous. So 0 to 50 is good air quality. And generally around here, our air quality is actually pretty good. Okay, we already talked about layers of the atmosphere. I'm going to go beyond that. We already talked about how ozone down below is bad, ozone up above is good. In the past, there's been too little ozone. That's my childhood. Anyway, so we're going to keep on going here. So how is ozone formed? How do we get ground level ozone? It's not directly produced. It doesn't exist there naturally necessarily, not in large quantities anyway. But you have to have the presence of sunlight and volatile organic compounds. So you take the carbon source of some kind. It could be carbon monoxide, methane, or some volatile organic compound. Volatile just meaning in a gas form. And organic compounds all are made up of carbon and hydrogen. So then you take it and you add to it an oxide of nitrogen of some sort, usually NO to begin with. Add in sunlight, and you produce ozone, among other things. And of course, ozone becomes a visibility issue, and ozone can affect plants and so forth. And again, the stomata. So I'll go through this quickly. You can always pause it if you want to look and read each slide. We already kind of discussed that. All right, so here's the actual series of equations. So you take the carbon monoxide plus this hydroxide ion, and it produces CO2 and hydrogen. Then you take the hydrogen and combine it with O2, and you get this hydroperoxyl radical. Okay, I don't know if you've ever heard of that or not, but you take that, add to it the car exhaust NO. The CO, of course, comes from the car exhaust as well. Add to that the nitrogen monoxide, you yields the OH plus the NO2. Then you take the NO2 and you knock sunlight against it, which knocks one of the oxygens free. And then now you've got, of course, this free O2 in the atmosphere with O running around looking to react with something, and you end up with O3. So this is how it's done. And so it's actually quite a process to produce the O3, but it does get produced. Anyway, we're going to move through here. The bottom line, O2 is usually pretty happy by itself, but when there's another O around, another oxygen floating around, especially one that's by itself, those are very reactive. Okay. All right, some of the carbon sources are these, of course, I already mentioned them. All right, we move on here. This is just looking at outgoing radiation. All right, so there is a video here about how the ozone monitor works. I'm going to post the basic version of this spreadsheet, of this presentation. You can go and watch the video if you want. I'm not going to play it here right now, but it tells you how the monitor works that we use to collect it. But bottom line is there's a photodiode that's emitting UV light, and as the air is pumped in from the outside, it interacts with the UV light. And as you know, ozone blocks a certain amount of UV light, so it knows how much light is being produced, and then it measures the difference between the light being produced by the meter, by the photodiode versus the known amount of light versus what actually is detected, and that's how it calculates ozone using this equation here. So it's a relatively straightforward piece of equipment. All right, the other five. So nitrogen dioxide, nitrogen oxide, and then of course N2O. N2O is a big greenhouse gas, much worse than CO2 and even methane. Well, it's just as bad as methane, really. And N2O is also an important product of power plant emissions. Of course, NO2 and NO are both the result of car emissions and truck emissions and power plant emissions as well. So the bigger one, though, the big problem is the NO because it's so reactive. Sources of this is in England in 2011. This is just one of the charts I could find, but most of it comes from on-road gasoline and on-road diesel, and that's no different here, really. Here's off-road diesel, other fuels. So you can see electric utilities. It's all from combustion of fossil fuels. I mean, so here's the thing: you get rid of fossil fuels to help the climate change issue. Guess what? You're also going to help the air pollution issue pretty significantly as well. Bingo bango, 2-for-1 deal. Kill two birds with one stone. However you want to put it, it's a good thing. But getting off the fossil fuels is the hard part. Okay, but carbon monoxide, CO. Here's looking at using the NASA Terra satellite in the months of April, May, and June of this particular year. Again, this was 2011. You can see where carbon monoxide is most intense, especially in the mid latitudes. Notice in the southern mid latitudes, you don't have the same effect. And that's because the time of year this is looking at is April, May, and June. And of course, this is spring. And of course, most of the industrialized countries are in the northern tier. So there's a couple of things going on. Part of it is just the tilt of the Earth, which is, of course, largely, I mean, it should actually be largely irrelevant here because it is spring. But still, most of the industrial activity is going on in the northern tier here. But look at China, look at Asia. I mean, look at all the carbon monoxide, and then look how it spreads off of China, and so forth, and blows right over Japan and the Koreas, and comes over here and hangs over us. Now we're producing some of our own, but we're breathing a lot of Chinese carbon monoxide as well. So that's something worth keeping in mind. Most of the CO comes out of transportation, and then of course after that, forest fires. The rest of this stuff, fuel combustion, is really looking at wood fuel, and power plants and industry and so forth. But so, transportation and forest fires are the primary sources of CO. Particulate matter. Particulate matter, here's some beach sand, is about the size of small, fine beach sand or human hair. Well, actually, human hair is actually, I had that wrong earlier, apologize. You can actually fit 5 10-micron particles. So a human hair would be 50 microns thick, and then these 2.5 particles are even smaller than that. You really can't stop yourself from breathing these puppies in. I mean, they're just going to be breathed in, right? I mean, how much can you stop with a filter? Even a really great HEPA filter? It's a really good question. And it's really, the more expensive the filter, the better it is usually. Well, one hopes anyway. Always look for data when you're looking at buying filtration mechanisms. But anyway, these are some examples of particulate matter. It's not just one single thing. It's a variety of things. I mean, look at the broad spectrum of things. And the most concerning ones are, of course, things like these metals. And then, of course, some of these other secondary aerosols that can also be considered particulate matter. So it's a package of stuff, okay? A package of nastiness. Here's from 2003 to 2011. This is a modeled general view of particulate matter at the 2.5 micron level size. On average, this is where the most particulate matter was located over these industrial areas and so forth in the eastern part of the U.S. And then over some of these areas of California and Utah, my guess is that some of them are. This is, of course, due to dust and things of that nature. But significant. I mean, this is significant amount of particulate matter. So, all right. Now you'll note. Let's look at lead. You may remember lead being an issue in Flint, Michigan, in the water, but lead's historically been an issue in the air. Now, granted, look at lead in the air. If you look at lead used in gasoline, that's really dropped off. But how could you connect gasoline to average blood levels, right? Unless, because nobody's drinking the gasoline, because that's going to kill you. Don't get any ideas, guys. So if you drink gasoline, it'll kill you. So there's some other way. Is clearly there's a relationship. Well, I say clearly, correlation is not necessarily causation. However, in this case, there definitely has been. Here's another piece of data that's from another study looking at the murder rate, actually, and then gas lead tons per 1,000 population. And you can see that there is actually something going on there. People were being affected by the lead in the gasoline. Why was the lead put in the gasoline? Well, here it is. Tetraethyl lead was used in early cars to reduce engine knocking, boost octane, and so forth. So it was all to help the mechanics of the engine. And it was obviously, you'd look for, here's an example where they're marketing, some marketing for that. It's like cigarette marketing. But back in those days, we didn't think lead was a problem. Now we know better, but we didn't know better then. So this is quite an old ad going back to the 1940s, probably. So you think about, would you want to go back to the 1940s? Would you want to go back to a time when you were breathing lead in large quantities from the air because of gasoline? That's a really interesting question. I would say no. I think back to that, and I just don't want to be a part of that. Sulfur dioxide, again, this is a NASA image, and you can take and look at where the sulfur dioxide is, and you can pick out power plants. So here's obviously some some big power plant production. There's a lot of coal-fired power plants into this part of Pennsylvania, Ohio, West Virginia. And all that, of course, blows over us because that's where the wind comes from. So anyway, those are the 6 criteria pollutants, and it's important to know what they are. We're going to get into we'll look at some more data, sort of wrap things up. We only have a couple more days we'll spend on air pollution before we get into talking about the sources of building materials. That's our next topic. But hopefully you get some idea about the importance of air quality, not only exterior air quality, but then just start thinking about it as an interior issue, because these gases don't just stay outside, they come inside. And then when you're inside, you have all these manufactured products that also off gas. And so how do you chemicals? So how do you manage to keep indoor air quality really, really high as well? All right, well, hey, it's been a pleasure as always. I hope you weren't completely bored, but we will talk more. By the way, look at the Ohio River. Look at all the power plants along the Ohio River. Dang, that's a lot of power plants. I grew up here, right? So anyway, you guys have a great afternoon or morning or evening, whenever it is you're looking at this, and we'll talk to you soon. Until then, toodaloo.